So before we get started today, I got just a few things I want to talk about. If you didn't notice, if you didn't check Piazza or Autolab, the first round of learning objective assessment for the first learning objective program execution is out. It's on Autolab. If you go to your gradebook and then click on your score, you'll be able to see some the feedback that I provided. I spent my whole Saturday doing this and wrote feedback for every single student, so make sure you read it and see what I have to say for you. If you completed the learning objective, the feedback is just like, thumbs up, good job, keep up the good work, something to that effect. If you didn't complete the learning objective, the feedback is like your next step, so something you can do to remedy the situation. So I'll repeat this again just to be clear. If you didn't get the learning objective, that doesn't mean you're done with the course. It doesn't mean you should go resign. You'll have lots of opportunities to make up this learning objective and show me that you did complete these 3 bullet points, that you can do these 3 things before the end of the semester. In worst case, you're going into that final exam trying to check off a few bullet points, a bullet point or 2. You always have more opportunities. Just a few specific pieces of feedback I wanted to mention. Some of you, I said, just finish up your lecture questions, and once you finish those lecture questions, you'll have this objective checked off. That's one way that you can solve that you can complete the lecture objective. That's the easiest way. Finish those lecture questions, done with it. If you don't finish those lecture objectives, that doesn't mean that's it, you're done. There are other lecture questions you'll have, there are other activities, there are other things that you can do later in the semester to show that you completed that. That's just your one option. If you want immediate action, you want to get this off your to-do list immediately, finish those lecture questions, done. One of the other big pieces of feedback was if you didn't get the 3rd bullet point, the stack and heap, stack and heap memory diagrams that we did in lab. Again, I can only test that in lab. I don't have, I shouldn't say that, but I can't test those in an automated way through lecture questions when I'm asking you to trace through program execution, what's happening in memory. But there will be other opportunities to solve these, to complete those in lab to show that you understand the stack and heap. So if you didn't get that, keep studying, study the stack and heap, get a good understanding of where values are stored in memory, and how those references are stored on the stack and move around your program. And when we do the 3rd learning objective, when we talk about immutability, and during the 4th learning objective, when we talk about linked lists and trees, we're going to be bringing back stack and heap diagrams. Those are the topics that will be important when we talk about both of those topics. And during those lab activities, you'll have more stack and heap diagrams that you'll be drawing. So if you focus on the material, keep moving forward, keep studying, and during those activities, you do well on the stack and heap questions, then I can go back to the learning objective 1, check off bullet point 3, done, and then you can knock both of those off. So just keep focusing on the content, and you can naturally get that checked off later on in the course when those come up again. Same are true for the first 2 bullet points. If I say complete these lecture questions and you'll complete this learning objective, but maybe one of those lecture questions you sunk a lot of time into, it's just not gelling well with you. Something about the question, there's just some sort of disconnect between the question I wrote, maybe it's worded in a strange way or whatever it is. Something's really jamming you up on that specific question, but you know you understand the concept. Maybe you know you understand references and how they move around your program, but these battery questions just aren't doing it for you. Well, there will be more lecture questions, there will be more lab activities. Especially being the first learning objective, a lot of the content later in the course is going to depend on those 3 bullet points. So you'll have a lot of opportunities to do something more complex that applies that material in more unique ways. Well, if you can do that, I can go back to learning objective 1 and check those things off. So if you're really struggling, maybe there's one incorrect solution that you just can't get, but you know you understand references and you know you understand testing, don't be afraid to just cut your losses on that specific question, refocus on the content, and then just naturally have that checked off later as you do something more complicated involving testing or references. And just to reiterate, your goal is to show me that you can do those 15 bullet points in the course. I'm not too concerned with the way that you show me, just you got to show me that you get those 15 bullet points, that you can do those 15 things. So I can check those things off and then have those done. So if there is a specific thing, I want to make sure I gave everybody at least some actionable thing. This is what you can do immediately to start fixing this situation if you got a 0 on that. But that doesn't mean that's the only thing you can do. The worst case, you're showing up to that final. Potentially, somebody could show up to the final. I don't recommend this, so it's probably not going to work. But theoretically, someone could show up to the final with 0 out of 15 bullet points checked out and get all of them on the final exam. I don't see it actually happening in real life. You would have gotten at least one of those checked off if you can do all those things. But theoretically, it's possible. So no one's ever out of the running for the class. I think I got everything. Any questions about that? I think that's what I want to say about it. Yes.
So for the actual grading of the course, the application objective questions, so like the rhyming dictionary or the physics, if we don't exactly get a 1, does that mean it's like...
So that's the next big thing I want to talk about. That'll be the big thing, yeah. I will answer your question in detail. Any other questions about learning objectives before I go into that? Let's talk about this. So I've been talking a lot about the learning objectives. Whenever I talk about something about the course structure, it's usually about learning objectives so far. And I've been giving that a lot of focus because I have this, what looks like a very strong stance. If you just read the syllabus, it's 5 or nothing. Like you got 5 or fail. You get all 5 of these learning objectives, or you fail the class. It's a very strong stance. So I want to constantly reiterate that no, it's not as bad as it sounds on the surface. You have lots of opportunities to show me that you can do those 15 things, that you've completed those 5 objectives. But I haven't talked much about the application objectives because, well, you're moving up your grades, you're earning more grades with that, but it's less critical than the learning objectives, less critical than do it or fail. But now's the time. I want to take some time, and I probably admittedly should have talked about this, took some time to talk about it before the first homework deadline. But the homework objectives. So we have the homework assignment with a deadline, and then the verification lab, which will be this week. If you didn't complete the homework assignment, it doesn't mean that you will not get that application objective. And that's the part I should have made more clear before the assignment. If you don't complete it and you don't get credit for that application objective, as long as you made an honest attempt at the homework assignment, it'll be similar to the learning objective feedback, where I'll give you some feedback and say, you didn't get this application objective, but here's what you can do to complete it with some later deadline. So I'll give you some outlet, some method to be able to remedy that situation. If you didn't show any effort, if either you made 0 submissions or you submitted something that's just like random hits on your keyboard or something, you just put absolutely 0 effort into it, that's going to be a 0 and you're done. That's it. You're not playing for an A anymore. You're aiming for an A- at that point. There's just no remedy for that one. If you have some effort and I determine that you actually made an honest attempt to solve the homework, but you hit a roadblock, even if it was fairly early, maybe you completed objective 1 and got halfway through objective 2 or something like that. Not looking for too much here, but just something to show me that you were participating in the course, you were trying to complete this assignment, but I don't know, maybe something came up and you had some legitimate excuse, so you just couldn't give it the time that you wanted. I don't care what it is, but as long as you've made some effort to work on it, I'll give you something to work on. On the other end, if you completed the primary objective and lab this week goes well, you're probably just going to get full credit. You're going to get the credit for the application objective. If something goes a little bit wrong, maybe you got the 3 testing objectives but couldn't quite complete the primary, lab goes well, or maybe you completed the primary and lab didn't go so well, you just couldn't explain anything about what you did. In those cases where you're close, that's where I'll say, okay, finish up whatever you're missing, or come in for another demo. Show me that you can explain and understand your code and understand what you just did on this assignment. There might be some feedback like that. I don't know what exactly it'll look like because it's going to depend on all the situations. Once I have all the lab submissions, all the lab demos, all the lab quizzes, once I have everything in front of me, looking through everything, I'll make those decisions for specific situations. But there'll be something where I'll say, okay, you can do this by this date, finish this up, and then you'll get credit for the application. So if you're close, I'm going to give you some feedback. Finish it by some time, some later deadline. If you're not close, or if you are close, but you want to choose this option, I wouldn't recommend it. If you're close, just finish it up. But if you're not close, one of the options I'll give, so I don't know the specifics of all of the situations, but I do know I'm going to end up doing this one. As there were 2 homework assignments, you tried one, you didn't get very far, I'm going to say do the other one by some deadline, by some later deadline, and that'll be how you can get that application objective. I feel like there was one more thing I needed to say, but I feel like I got it all. Any questions on that? Did I miss anything? You wouldn't know if I did, would you? Yes.
I guess with the application objective, it's like when you get the 1, you can still miss a bunch of test cases.
Yeah, those are fine. I've got a lot of questions about that. If you got the primary objective, my stance is if you got the primary objective, that was the goal, and the rest was scaffolding to help you get there. If you didn't really need the scaffolding, who am I to say? There are many students this applies to, but I'll say it anyway. Like if the concept might apply later in the course, but like if you didn't get the testing bullet point and the learning objective, and you also skipped a bunch of the testing and homework, like that was one more opportunity you could have shown me that you can do testing if you skipped that opportunity. But there were students who didn't finish all the lecture questions, and they got the reference questions, but they missed 1 or 2 of the testing questions, but they did the homework and got all of the testing objectives there. I was able to say, okay, you got this learning objective. I don't need to see those lecture questions because you did something way harder over here applying the same thing. So for the application objective, it's just the primary, but you can use those other objectives to help yourself elsewhere in the course. And also, if you don't get the primary, if you're just like, oh, he said I don't have to do the testing objectives, I'm just going to aim for primary and skip all the testing, and you don't, even if it's just one tiny thing you don't finish on the primary, well, there's not much I can do for you there. You're going to be in the attempted but not even close category. So to reiterate one more time, my whole goal with all this this grading structure that isn't clear yet, I want you to be focusing on the concepts. Focus on the concepts, learn the concepts, understand the concepts, and be able to actually do those 15 bullet points. And at that point, it's my job to see that, to look at your work, and see the evidence of that, and give you credit, and give you the grade you deserve, based on what you can actually do. I don't want you to get jammed up because of some percentage-based grading structure with points and all this stuff, and something silly just prevented you from getting the grade that you actually deserve, and the grade that reflects what you actually learned. On your grade to reflect what you've learned and taken away from this course. So that's my goal. If you don't feel like I'm meeting that, if you do really understand you can do those things and you're not getting the credit for it, come talk to me. Let's chat about it. We can get to the bottom of it. All right, any questions about course structure, grading, or any of that? Let's talk about the state pattern. Okay. Let's shift gears here and get some new content. So the lecture question today is going to follow the same rules as the current homework assignments, calculator and microwave. Let's make that. I'm not going to wear it if it ain't going to do anything. So we're going to follow the same rules as that, in that there's no control flow allowed, no conditionals, no if, no switch, no case, no while, no for, no loops, none of that. No control flow allowed for this assignment. So how do we accomplish things without control flow? And today's, Wednesdays, Fridays, lecture questions, and of course the homeworks are all going to follow the same criteria. They're all going to be about the state pattern, and they're all going to ban control flow. If you submit with control flow, AutoLab's going to just spit it back at you and say, no, this isn't cool. What I do is I find and replace all the keywords that have control flow, the ifs, the else's, the for, while, any keywords. I'm going to find them and replace them with redacted with a bunch of stars around it. So if you see that in your assignment, it means you use some banned control flow. can't use that. So I'll do the find and replace and then compile your code. So you're going to see your compiler errors, whatever compiler errors there were when I tried to compile your code without that control flow in there. So with that, we want to implement a player class. We're going to do a little bit of simulation of a 2D platformer. Suppose that this isn't restricted, it could be 3D. But it's going to be somewhat similar to the jumper game for the physics homework, which Wednesday's lecture is going to be all about that, the jumper game and how the jumping mechanic works in that game, which uses the state pattern. It's a fairly involved application of the state pattern. So if you did rhyming dictionary, I recommend, I've said this before, but I recommend at least taking a look at the physics engine assignment, clone the repo, take a look at that code, and get an idea of what's in there so you can follow along better in Wednesday's lecture. You'll get more out of the lecture if you take a look at that code beforehand, because we're going to look in depth at that. For this lecture question, let's look at a much simpler application. It's only your first stab at the state pattern, so it's not going to be too crazy. But let's implement these 5 methods where duck, stand still, and run can change the state of this player. They can be in one of these 3 different states. And then depending on the state, this jump height and movement speed are going to return different values depending on whether we're ducking, standing, or running. So we have different behavior based on the state, but we have to do this without control flow. So we would like to say if ducking 4, if standing 3, else 6. That's what we'd like to do, that's what we would do, and that would be like a day 1 lecture question if that's what we were allowed to do. Now without control flow, how do we get this done? How do we have different behavior based on previous calls to methods without control flow? That's what we want to get. And if you submit with any control flow, it's Autolab's not gonna be able to grade it. That includes any of the files you submit, any of the Scala files you submit. So if you have all your code in one big project, just make sure you're only submitting this lecture question for today, and that'll be true the whole week. Just make sure you're not submitting the whole thing. If you submit your whole project with all of your lecture questions, Autolab's not going to be able to do anything with it. What you can do, just go into the package, the platformer package, zip up just that directory, and then submit that. That's the easiest way to get it done. That's how I submitted my solutions for testing the grader for this lecture question. Yeah, that's all I need to say about that. Any questions on the question? All right, let's talk about the state pattern. So the state pattern is what we call a design pattern. These are applications of object-oriented programming that solve specific situations that we come across often in programming. There are lots of them. I recommend, if you're interested, searching design patterns, or you can search the Gang of 4. These are the people who generated the first set of design patterns. They have quite a few of these that they said, these are common approaches that developers tend to take. Let's formalize this, give them names and all that stuff. Really useful patterns for certain situations. Each one has a specific situation that it's useful for. And that can be helpful. That can be pretty interesting to help you out a bit. We're only going to focus on the state pattern in this course. It's a nice application of inheritance and polymorphism. So we want to give a good use case for these things, for these topics. And what we want to do with all these, scalability, maintainability, being able to add new features, simply, that's the goal with a lot of these design patterns. State patterns, no exception. So the state pattern, we're going to use polymorphism to change the behavior of an object. So objects, as we know, can have state and behavior. And we usually want that behavior to depend on the state. So the methods that we call for the behavior are going to have different behavior based on a value of the state. Sometimes this is a simple mathematical function. If we want a player to throw a ball, that might depend on his current strength and the mass of the ball. And we have some mathematical formula function that we can apply to be able to figure out how fast that ball is going to be moving. So we have different behavior based on the state, the strength of the player, and the mass of the ball. But it's not big changes in behavior. We can compute that. So what if we want significantly different behavior? What if we want either to throw the ball or put the ball away in our inventory? those are two completely different things. We can't just have a mathematical formula to be able to tell which one of those two we're going to do. So naturally, this is what we do. We're going to say if some conditional, we're going to have this behavior, else completely different behavior. Basic control flow stuff, completely different behavior, completely different code being executed, different code blocks. And there's nothing really wrong with this approach. It got us this far, and it'll do us well in the future. And I forgot to mention this in the last lecture, but with this banning control flow, there's nothing wrong with control flow. I don't want to give that impression. I get those comments sometimes when we're covering these state pattern stuff. I only ban control flow to force you to use the state pattern, or else if I don't force it, unfortunately, very few of you will actually use the state pattern. You're just going to use all your control flow. If I ban control flow, it's an effective way to force you to use the state pattern, and I need you using the state pattern. It's a way where I can force you to use the state pattern, but also auto-grade things. So it's more of a convenience thing why I'm banning control flow. There's nothing wrong with control flow. I don't want to give that impression. But if I ban control flow, you have to use the pattern. And I'll do the same thing with functional programming. When we talk about immutability, I'm going to ban the ability to mutate variables. So var is going to be a banned keyword when we get to those things. There's nothing wrong with variables, but I want to force you to use immutability to see the difference between that approach. In the state pattern with object-oriented programming and immutability and functional programming, these are two very different approaches. There's nothing wrong with either of them, but they are kind of competing ideas, competing structures for your code. And to have you use those over the alternatives, yeah, I got to ban. I banned some things for the homework assignments. It's artificial, but that way I can force you to use the topic that we're learning in the course. And when you get in industry and have somebody say, oh yeah, we use the state pattern here, and you say, oh yeah, I didn't do that because I didn't have to. Anyway, but this will work. But what happens when we have a lot more functionality? What happens when we have this big else if, and a lot of different behaviors in this thing? This gets a bit more unwieldy, harder to work with, and harder to test. If we want to test a method with a big conditional block like this, we have to throw a lot of test cases at this. For each one of these behaviors, we have to write test cases that make sure that that conditional is true, and all the previous conditionals are false, and we have to have enough test cases with that that hit that conditional that test fully that behavior for that conditional. So we're going to have a lot of a lot of test statements, test cases to be able to hit every branch of our conditional, and have enough test cases on each branch to be able to test everything. This is going to be painful as this gets more complex. And then what happens when that test suite fails? That test says, hey, I'm failing over here. Where do you start looking for what exactly went wrong? On this input, it failed. Okay, now I got to look through all this code, figure out which branch was taken, which branch was supposed to be taken. It's going to take a while to do that, and especially if maybe you write this method and then a year later something happens elsewhere in your project that breaks this functionality, and you got to reload all this in your mind. What was I doing here? What was I thinking when I wrote this thing? It gets painful. Sometimes this is the right approach, and that there's nothing wrong with it. Sometimes it can get very complicated, especially when the behaviors are significantly different from each other. So this is where we're going to pull in the state pattern, and we're going to have the behavior of our object change depending on the type of one of its state variables. So usually we're checking a value to conditionally run code. We have an object with state variables. We're going to check the current values of those state variables, convert that to a Boolean expression, and if that Boolean expression is true, we're going to execute some code. If it's false, we're going to execute some other code. This is the basic idea of conditionals that we've been using so far, which is great. Conditionals are fantastic. With the state pattern, we're going to switch it up a little bit, and have different behavior based on the type of a variable. So we're going to have a state variable. And by the way, I'm going to say the word state so many times today, it's going to start to lose meaning. But there's going to be a state variable of a type that's an abstract class that's going to represent a state. And then depending on the actual concrete class that is currently stored in that variable, the current reference, the type of the object it's referring to, that type is going to have a different behavior based on the methods that it defined that it overrode from the base class. So depending on what specific type we have in that variable at that time of the method call, we're going to get different behavior out of that object. So this, and then we're going to write a separate class that extends our state class and implements all those methods for each different state we can be in. And then we're going to end up with a lot more, but smaller pieces of functionality, more classes, more methods, but each method in each class is going to be pretty small, pretty concise, and easier to reason about, easy for us to think about, to implement, and to test. So we're going to write that state class as an abstract class, define all of the methods that the state is going to be responsible for. We're going to extend that for each state that we can be in. Then each state, we'll implement those methods. And each state will also, we'll talk about this more once we get our heads around this a little bit more. But each state is going to have a reference to the object to which it is attached. We'll talk about the importance of that after we get a better feel for what the state pattern is. All right, so what are we talking about here? What is this actual state pattern? That's the technical definition over the last few slides and technically what's going on. But to make this more concrete, let's meet Bruce Banner. I'm sure most of you already know this guy, but if you're not a Marvel fan, he's a very great scientist, very brilliant. He can successfully drive a car, and we'll see why I mentioned that explicitly in a few slides. But he's not very good in a fight. If he's got your back in a fight, you're probably not going to do so well. But Bruce Banner can turn into the Hulk. The Hulk is great in a fight. He can really help you out. He cannot drive a car. He just smashes them, and he's pretty much completely out of control. Very different behaviors, same person. One man, two completely different behaviors, depending on his state. So how would we represent this in code? Well, we're going to have one Bruce Banner class that we're going to that's going to have a variable of a type of an abstract state, and then we're going to have concrete classes for each different state that he can be in, and we're going to defer to the state variable for the specific behavior. So let's take a look at some code and see exactly what that looks like. So let's create a Bruce Banner class, which my TO is picking on me. He said I said the same thing last semester, but really this should probably be an object of Bruce Banner. There can only be one Bruce Banner. But whatever, we'll keep it as a class because that's what your assignments, that's what you're going to be doing is creating classes of these things, of this nature. But we'll create a Bruce Banner class. He's going to have a state variable of an abstract state class that we'll see on the next slide. That's going to store whatever state he's currently in, whether he's Dr. Banner at the time or whether he's the Hulk. That's going to determine his behavior. And then the Bruce Banner class isn't going to have any actual functionality defined. It can have some. In your homework, you'll have some functionality defined in here. But we don't have to have any. We're just going to defer to the state for our actual functionality. So Bruce Banner, we call a make angry method. We're just going to call the state's make angry method. Call it calm down, we're just going to call the state's calm down method. Use car, we're going to call the state's use car method. And fight, just call the state's fight method. So we're saying, hey state, how am I currently behaving? And then the state is going to determine which specific implementation of these methods is inevitably called. So we have one state class, which is going to define our API. These are the methods that we're going to defer to the state for functionality. These are any methods where the Bruce Banner class is not taking care of itself. He's just going to defer to the state. Then we're going to extend this class with each state that Bruce can be in. So whether he's Dr. Banner or the Hulk, we're going to have two different states, two different classes that extend state, so they're of type state, so they can be stored in that state variable of type state, named state. I told you I'd say the word state way too much in this. I shouldn't have named the variable state. It's just a little too much. Anyway, so now when we write these methods, we're narrowing our focus a lot more. When we add functionality to this program, to this class, we're thinking, okay, when Bruce is Dr. Banner and somebody makes him angry, what does he do? And we'll talk about the make angry and the calm down over here. We'll talk about those in a minute. I'll table those for now. But when Dr. Banner, when somebody calms him down, what does he do? When he's Dr. Banner and he uses a car, what does he do? Well, he can drive that car. I didn't show the car class in these slides. It's in the repo, but it takes a Boolean which says if the car is being overloaded or not, whether we're going to do damage to the suspension. So he can drive a car and he's not going to do any damage to the suspension. Dr. Banner, what's he going to do when he fights? Well, not much. The Hulk, angry, doesn't do much. The Hulk, how does he use a car? He's just going to smash it. The Hulk, how does he fight? He fights quite well. And we're, of course, not building the functionality. I'm just printing things to the screen because, we're just simulating this. We're just talking about the state pattern for now. So each time we write one of these methods, we have a very narrowed focus, very laser-pointed focus. This is what we're writing. How does the Hulk use a car? And now when we want to test this method, we just create an instance of the Hulk class, call useCar, and check to make sure it had the functionality we wanted. That test is easy to write, it's easy to use, and if it fails, I know exactly where to look for my functionality, what could have gone wrong. I don't have to chase through a big conditional block to see where this thing is failing. And I don't have to create instances of the Bruce Banner class, manipulate its state to make sure that he's the Hulk, then give him a car, and then test with the car if it got smashed. That test is more complicated to write, and if it fails, it's more complicated to figure out what exactly went wrong with that. But this testing is easy. Yes, you have more tests, you have 8 tests, but each test is going to be simple. Very simple and straightforward. Okay, so in the Bruce Banner class, when we create a state, we're going to say he's initially Dr. Banner. So the state is Dr. Banner, and all 4 of these methods have the functionality defined in the Dr. Banner class. But when I created his state, I gave that state a reference to the object to which it's attached to. So the Dr. Banner state class needs a reference to the Bruce Banner class that it's attached, object that it's attached to. That way the state can access the state variables of the Bruce Banner object. So right now, with this class, we only have one state variable, so there's not much to access, but we will need to access this variable itself. In the state will have to access that variable. But we can add more functionality here. For example, for the calculator class, in the calculator class itself, most of the functionality you're deferring to your states that you write, but you will want some state variables to store the current left-hand side, the current right-hand side, probably as strings so you can concatenate to them, also as doubles so you can display them to the screen. You might want the current operator that should be used for the next operation, the next equal press, and a few other bookkeeping things. You'll want some state variables in there. And you want your states to be able to access those state variables, so we give it a reference to that attached object. Your calculator states will have a reference to the calculator to which it's attached. Your microwave states will have a reference to the microwave to which it's attached. And then they can access those variables and decide how to behave exactly based on the values of those variables. This is where we have to be careful with our references. We want to make sure that the object to which we're attached isn't changing. So we're attached to this Bruce Banner in our state classes. When we implement that functionality, we want to preserve that reference. If anywhere in our state we're saying new Bruce Banner, we're doing things wrong, unless there's some specific application that needs to do that. Whatever reference the state is given, it needs to always be working with that reference, or else we're not going to see any of that functionality to the outside world. And outside of this code, we'll build all this functionality with the state pattern, but outside of this code, other code is only going to interact with the Bruce Banner class. It won't even know or care that this is using the state pattern. It would just interact with the Bruce Banner class to be able to get this functionality. So if the state is not referring to that Bruce Banner class that the outside world cares about, then we're going to break a lot of functionality with that. So we got to be careful about our references. So each one of these states, concrete states, has that reference to the Bruce Banner to which they're attached. We'll assume there can be multiple Bruce Banners. Then I don't have to update my slides. One of the Bruce Banners that exists and we have access to the state variable, this named state. This variable is going to store the current state. As long as we're not jamming up our references, banner.state is going to be the same reference as this. If I did banner.state equal this, that should result to true inside these states. Because this is the object to which I'm attached. If I access the state of the object to which that state is attached, well, that should be the state itself. So this should be the same as saying this, the same reference as this. But we want to replace the reference stored in state, so it's not this anymore. Sometimes we want what's called a state transition. We want what's called a state transition. We're going to change the state on certain behavior. So if he's currently Dr. Banner and somebody makes him angry, we're going to change the state of the Bruce Banner to which we're attached to the Hulk state. So we're going to transition state to the Hulk, and now that Bruce Banner just replaced all of this functionality with all of this functionality. So all of his behavior just changed when we hit that state transition. Then we're the Hulk, we have all this functionality now, and if somebody calms him down, his state is going to transition again back to being Dr. Banner. He's going to transition back to that state, and all his behavior changes again. So we have very different behavior after these state transitions. We hit the state transition, the next call to one of these 4 methods, it's using these 4 implementations, which can be wildly different behavior after that transition. All right, let's take a breather right here. And, are any questions to this point? Okay. So, great. But there's a big argument you can make right now, and you probably win this argument. Excuse me. That application probably would have been a lot easier without the state pattern. We didn't need the state pattern for that. I'd say that we even made things a lot worse. Like we could have done that by having one Boolean name, something like is Hulk, and then for each of those 4 methods, just in the Bruce Banner class, just one class just said, if is Hulk, do this, else this. And it would have been probably, maybe a little, depending on your opinions, a little less clean, but you have everything in one file, everything's in one place. A little more complicated to test because now you're testing just 4 methods instead of 8 smaller methods. But we can do that, it's just a little organizational change. So not too much of a deal. So why did we add 3 more classes, 8 more methods, actually 12 more methods if you count the abstract ones, and all this extra complexity, and now anybody who joins our team has to know OOP and understand inheritance and all this stuff. Why would we do all this? Well, we haven't really leveraged the pattern yet. So let's see the true pattern, true power of this pattern once we start expanding the states. So meet Professor Hulk. So Professor Hulk is a 3rd state that Bruce can be in at any given time. And he has very different behavior from either Dr. Banner or the Hulk. He has the strength of the Hulk, but he's controlled like Dr. Banner. He just has different behavior. So how do we add him? How do we add this new state to our code? Well, it's really no big deal. We create a new class, Professor Hulk. We extend state. We implement those 4 methods. Adding a 3rd state is as much work as it was to add the 1st state. If we have 100 different states, so we have an object with 100 different states that it can be in, adding that 100th state is going to be as much work as it is to add that 1st state, or the 10th state, or any other state. We create a new class, we extend that abstract state class, and we implement all the methods, all the abstract methods. That's it. So it's the same thing that we did for the other 2 states. When he's Professor Hulk and someone makes him angry, what does he do? When he's Professor Hulk and someone calms him down, what does he do? When he's Professor Hulk and he uses a car, what does he do? Well, he can still drive it now, just like Dr. Banner, except he's going to do some damage to the suspension now, so we're going to set overloaded to true. He's going to do damage to the car. If he fights, he's going to be able to fight very well. So we just add that. Bam, new state, no big deal. If we had our if is Hulk, do this, else this, we have to restructure that entire approach to add this 3rd state. Now we can't store is Hulk in a Boolean. Do we have some string where we're going to store the state? Then we're going to do some string comparison and make sure that we spell it right on every state transition. Like we would have to rethink our entire approach to the problem at that point. Reorganize a lot of code, change a lot of code that's already been tested, which means we have to retest that code. We have to write new tests. There's a lot of work that would be done to expand that one. With the state pattern, not so much. New class, test these 4 methods, and then add our state transitions. The state transitions is where we might have a little bit of extra work. I'm avoiding it here by putting in the Bruce Banner class, but we might have state transitions in our other states. So we might have to change a little bit of code in those and then retest those methods because our expected behavior has changed, but not to any significant amount. Here I'm going to avoid that by putting this learn control method inside the Bruce Banner class itself. So if we have functionality that we want to be the same across all states, we'll put it in the class that has the state itself. So learn control, doesn't matter what a state is, we're going to transition to Professor Hulk. So we can do this as Dr. Banner or the Hulk. You can learn to control himself and transition to Professor Hulk. In there, we're not going to defer to the state for those transitions. And notably, once he's Professor Hulk, there's no state transitions away from Professor Hulk, so he's stuck there. He can't go back. He can't forget how to control himself and go back to being the Hulk. Oh, I gotta mention this on the previous slide. We said all that. All right, and finally, a good way of visualizing this, because this can get complicated when we have a lot of states and a lot of transactions between the states. Writing each state is simple, and testing each state is simple. But once we have a lot of interactions between states, it gets helpful to visualize it with something we call state diagrams. For this, we're going to have each state represented. Here, I just represent them as squares. Each state is a square, and then visualize all the transitions between them. So which method calls are going to trigger a state transition? So initially, we're going to be Dr. Banner. If somebody calls make angry, he's going to transition to the Hulk. Someone calms him down, he's going to transition back to Dr. Banner. And from either one, if someone calls learn control, he's going to transition to Professor Hulk, and he's stuck in that Professor Hulk state after that. So there's just a nice way of seeing the top level organization of the code. You have a state diagram, maybe you have 10 states that things can transition around. You have a new person joining your team, you got to catch them up to speed. You start with a state diagram. Here's the top level planning of this object that has 10 different, wildly different behaviors. Here's what we're thinking, and then when they look in the code, they can figure out, okay, this is what each state does. I know how they transition between each other, and start getting the picture of how it all comes together to have this complex behavior organized in a better way, easy to get up to speed, easier to extend, most importantly. I shouldn't say most importantly, but very importantly, easy to add new features. It was no big deal to add this third state, and we could add all kinds of more states to this. All right, some tips on using the state pattern for these 3 lecture questions and for your homework. Some of how to approach these problems. You don't have to follow this exactly. This is my advice, though, is to start with the API. What method calls are you going to defer to the state for functionality? For the homework assignments and for the, there's some decisions to make for the current lecture question. But for the homework assignments, this is pretty straightforward. They're the ones already in the object that I wrote for you. The API is pretty much there. You're going to want to defer all of those button presses to the state for the specific functionality. Except, I guess, the clear button, you might not need to defer to the state. Well, I don't want to give away too much, but in the microwave, you won't be able to do that. But anyway, you'll be safe if you just have all of those methods be the API. But first, figure out which methods you're going to defer to your state, which methods are going to change behavior depending on the current state, and then decide which states you'll need. Any situation with a different set of behavior is going to need a new state. So for example, with the calculator, you're punching in a number, you're having a good time, and you hit the decimal button. That button is going to have different behavior depending on whether it's been pressed already or not. So the first time you press the decimal button, you want to add a decimal to the number. But if you push it again, you don't want to add another decimal because then you're going to get a string parsing error when you try to convert that to a double. So we have behavior that's going to change, so we're going to need a new state. Whenever you have something like that where you're tempted, you'd be tempted to use a conditional, is my rule of thumb. If you're ever tempted to use a conditional, probably means you need another state. So you would be tempted to have a Boolean that says, have I pushed the decimal button or not? When you push the decimal button, say, if I haven't pushed this yet, add a decimal, and then mark that I have set that Boolean to yes, I have pushed this. And if it's already been pushed, do nothing. So you'd be tempted to have a conditional like that. That's the normal way. That's the approach that we would usually have. We can't use a conditional. So it's a good sign that we're going to need another state, and a state that says the decimal button has already been pressed, and override that decimal button press with just nothing, just the empty body. This should have no functionality anymore because it's already been pressed. And then finally, determine all the transitions between the states. You have all the methods that you're going to defer to the state for. You have all the different sets of behaviors for those methods and a separate class for each one of those sets of behavior with all the proper implementations. And finally, just the transitions between them. How do I move between states? Which button presses on this calculator or on this microwave are going to get me to this state? What's going to move me from this state to this state? Just deciding all those transitions and then replacing that state variable for each transition. So that's my recommended approach to tackling these problems. So for this question, what's the functionality that I want to defer to the state for? Actually, no, it is all of them. Probably just going to be all 5, right? What am I going to defer to the state for? What states do I want? This one, again, pretty straightforward. It's in the question itself. Ducking, standing, and running. We have 3 states. And then implement the behavior for each one of those states. Then the state transitions. Some of these transitions can't go between each other. We can't go from ducking to running. We can't go from running to ducking. We have to move through stand still in the meantime. So what are all those state transitions? And build out those states to be able to do this with no control flow. Any questions? All right, let's see everyone Wednesday.